Hello, everyone, and welcome to an excellent episode of Dr. J's Data Structures modules. For this module that I am creating primarily for my students that are through the institutions with which I work, but hopefully it will help others as well. So this is on Big O and asymptotic analysis. It's just kind of a short rundown. I've provided the document for you as well. So we're just going to go through this briefly, and hopefully it makes some sense, and maybe I can clarify some stuff if it's not clear by just reading it. So first things first, the question is, what is efficiency? So the efficiency of an algorithm is the time that it takes to run the algorithm and the amount of memory that the algorithm causes the program to take up. Okay, so these are our two major measures of efficiency. It would be time and the amount of memory. Specifically, we're talking about random access memory, or RAM. So that's what we call the volatile memory, the memory that basically whatever's in it is what's being used by the current programs, and if the power goes out, typically whatever was in RAM is just erased. So respectively, these are called, the complexities are called the time complexity and space complexity of the algorithm. For our purposes, we're going to focus on time complexity as it's easier to analyze. In order to determine the efficiency of an algorithm, you may be tempted to write the code and run it, and then time it for a few different runs to try to see, well, how fast is this code? Or maybe you write multiple examples of the code, multiple algorithms that are supposed to solve the same problem to see which one's the best. And that's fine and dandy, except for the fact that that could take up quite a bit of time just to come up with the code and to run it and everything like that. So you have to implement it. This type of analysis is valid, and it's called runtime analysis, but it has these drawbacks. So I briefly mentioned one of them, but if you run it on your computer and then someone else's who has a noticeably higher memory or lower memory and or higher or lower CPU speed, amongst other hardware factors, and also what other programs do they have running, you probably won't even be in the same ballpark as far as how much time these algorithms are taking. If you run the algorithm on the same computer at different times, you could even get significantly different running times because of other programs and other factors on the same system. And, of course, in order to run an algorithm, you have to have implemented it. So that takes a tremendous amount of time as well. And if there are many competing algorithms, you may find that you have to implement several to determine which is the fastest. So it seems like there should be some sort of motivation for finding a technique that we can analyze the efficiency of an algorithm before we take the time to actually implement it. And also that it should be independent of a particular device or system or time that you're running it. Okay, or when you're running it is what I mean in that respect as far as time's concerned. And this is where we get Big O. So the most popular technique for analyzing the complexity of algorithms is to use Big O analysis, also called asymptotic analysis. You can refer to the book. Now, if you're not coming from one of my classes, you may not know which book I'm talking about, but pretty much every book on data structures and algorithm is going to have some sort of information on Big O. We will discuss the more practical and calculation-based features that will appear on tests or assignments in my classes, and may occur in yours, even if I'm not your instructor. In order to perform a Big O analysis, you should know that the following are the most popular Big O complexity categories, in order from most efficient, which means the least complex, because we're dealing with what we call complexity, to least efficient, which are the most complex, or that take the most time given the same size of input. Okay. This whole thing is different from what we would call computability. Computability is the question in computer science as to whether an algorithm can even solve a problem or not. And there are situations where computability, where a problem is just simply not computable. It's not decidable. Examples you might have if you're taking a more advanced, maybe discrete structures, discrete mathematics course, or theory of computation. If you're joining us from there, they will discuss are there certain algorithms that a computer cannot solve? And the answer is yes, there are. One of the most famous is the halting problem, but we're not covering that in this lecture. This lecture is not dealing with computability. We're assuming that whatever we're dealing with is computable, but the computability has to do with theoretical and reality, but complexity has to do with, is it practical? Even if it is computable, then we ask the question, is it practical, or how long is it going to take to compute something? So we can think of each of these as a set of algorithms, not a single algorithm or a single solution. And I'm using the term set specifically. Okay, so you may have brief understanding of set theory, or maybe you've never touched it before, but a set, at least a basic notion of a set, is that it is itself actually a data structure, but it's also a structure that can be used in mathematics, and in this context, what we're dealing with is maybe a sequence or set, or, well, using set in the word doesn't help, a sequence of items or a collection of items that don't have any duplicates. Well, in this case, it would probably be closer to multi-sets, because you could have duplicates, I suppose. But you would have this right here, big O of 1, big O of log n, big O of n, etc. Each of these is considered a set, and each set contains different elements, just like an array or some sort of thing you've probably dealt with before, some sort of data structure. But the question is, what are the elements of these sets? And the elements are basically problems. And you could even think of the set of algorithms as well. So the algorithms that solve the particular problem are the elements in this set. So different algorithms can be put into one of the above sets. The value of n in any of these is what we call the problem size. It's often the size of a collection, such as an array that's being processed in some way. Big O of 1, that is constant time, suggests that the time taken for processing with a particular algorithm is independent of the size of the problem. So for example, if you have to process 10 elements versus a million elements, the runtime of that algorithm, if it's a big O of 1, will be negligibly different. But if it's something like even log n or n or one of these higher order sets, then you would find that the algorithm actually does take longer to complete. So the formal definition of big O, here's your mathanese for the evening. Don't get lost in the sauce here, and don't ignore it, because this is actually very important that you understand this. So the formal definition of big O, which should clarify the meaning of asymptotic in the alternative name, asymptotic analysis, is as follows. So we say that a function f of n, now I'm going to read it, it's going to sound very mathanese, and you may not get it or may not fully understand it, but we'll do examples, we'll try to work through it and understand what it means. So the formal definition of big O is that we say that a function, f of n, okay, we're talking about some sort of function, okay? We will talk about what function we're talking about. Don't think necessarily in terms of just a programming function. Think of it as something that is growing with the input size. So the function of time or function of space is usually what we're dealing with. So we say that a function f of n is big O of g of n. Sometimes in a book you might see the equal sign, or you might see a similar to sign, or something like that, just to show that the f of n is in this set. I don't like the equal sign because it implies that these are two equal functions, and that's not really what it is. Big O is even though it looks like it's a function call, big O itself is a set of elements. So we say that a function f of n is big O of g of n, okay, and that g of n is usually one of these things. Okay, so it could be 1 or log n, or g of n equals n, g of n equals n log n, g of n equals n squared, etc. So it's one of those. We say that f of n is big O of g of n if and only if the following holds. So we say that that function that we are interested in finding the big O of, f of n, its growth rate is less than or equal to a constant c times g of n, for all values of n greater than some value n naught. Okay, f of n is less than or equal to c times g of n, some constant scaling this thing in the parentheses, It could be 1, and it could just be this, like one of these. But it could be like 3 or 5 or 7.8 or something like that. So then you'd get, if it was linear, for example, you would have something like 2n or 5n or 7.5n or what have you. That's that c in front of that n. So we're saying it's being scaled somehow. And that's going to cause how fast it grows to change as well. But it's still going, the major thing that's going to affect it is which one of these. For example, an n cubed is going to grow way faster than an n squared eventually as n gets very, very big. Okay, so we're really interested for values as n gets large. So n is the variable problem size, and n sub 0 is the minimum problem size at which this inequality holds. So this does not, this basically puts a restriction or a constraint on this definition here that says that there could be places where your function is actually the same or bigger than whatever this thing is, but at some point, the value n is going to get bigger than n naught. Okay, so the size of the input is going to go past this threshold here, and then it's never going to look back. It's always, this function's always going to be bigger than the one on the left. Or said the way it's written, this one on the left is always going to be less than, or at most, it's going to be equal to this c times g of n on this side. So typically, we say that the c is some constant that can be multiplied by this g of n, and n sub 0 is that threshold, that minimum problem size. And we would say that the c can be multiplied by the specific value of the complexity category to make the inequality true. So g of n will typically be one of those categories listed above, one of these in the table. The g of n specifically is the thing in the parentheses. So big O of g of n would be like big O of 1, in which case g of n is 1. Or big O of g of n would be big O of n log n. So we would call it linear logarithmic, or linear arithmetic is another term for it. In which case g of n would be n log n. Or this one over here, g of n would be 2 to the power n. That's exponential. So don't get lost in the mathenese of the inequality above. All it says is your algorithm is represented by a function f of n, and the algorithm is big O of g of n. This is a definition. Does it belong to that set called a big O of g of n? If and only if it is bound from above by some constant c times that function g of n. So an important note is that we aren't concerned with all values of n, just as n becomes large. So there may be values for n for which this inequality is not true, as I mentioned before. But once it becomes true, while n increases, it stays true. So this is where the asymptotic part of the analysis comes from. Intuitively, you can usually just go with the largest growing term in an expression for the big O. So the following expressions represent different algorithms are true, okay? So, or the following expressions representing different algorithms, sorry. So right here, if I see 3n squared plus 5n plus 7, I would normally just say that's big O of n squared, because n squared is the fastest growing term. You don't say it's big O of n squared plus 5n or 3n squared plus 5n. You disregard constant coefficients, and you disregard the smaller terms when we're talking about what set does it belong to. Because relatively speaking, these grow a lot slower than the quadratic term in this case, okay? And down here, this is a simple one. So 3n cubed plus 2 is clearly big O of n cubed, because n cubed is the fastest growing term there. 2 doesn't grow at all. The ones down here, these are all potentially kind of fast growing terms. We've got an n squared here and an n to the 5th and even an n to the 10th there. Not sure what kind of algorithm would have 15 n to the 10th, but we're just dealing kind of in generalities at this point. But this is the largest growing term of all of them, so we would say this is big O of n to the 10th. And notice it isn't one of our common categories, but it is possible because that would be the largest growing term. So that's an intuitive notion of it, and that part's relatively easy. However, if you're asked to prove or write a proof of the big O, that's a different story. For some of you, you might have just got chills up your spine because you hate proofs, but don't worry, this is a little bit easier than probably what you're used to. You can't just say looks good to me in mathematics. Math is much more rigorous than a lot of other disciplines. Proof in a courtroom, for example, in law, paralegal, things like that, proof in a courtroom is going to be quite different from proof that's expected in biology or engineering or mathematics, right? Mathematics is we need a very rigorous proof. Engineering, we really like to see that things work. Biology, you might have some statistical proofs or also some practical evidence, and then proof in a courtroom is just beyond a reasonable doubt if you're in the United States. But don't worry, even if you don't like those geometric proofs that you might have done in geometry or trigonometry or maybe calculus, you might have done direct proofs and inductive proofs and things like that. The proofs that we have to provide for Big O are actually fairly simple in most cases. So this is our first thing that we need to do. Okay, we're going to be doing a couple different things in the remainder of the slides, but for right now, this is what we need to do. So we've got to remember the definition of Big O here. Identifying the parts, again, f of n is representing the algorithm we're analyzing. That's usually what we're going to see as a t of n, because we're dealing with time, so we usually use t. S of n would be for space, which is our memory that we use up, but often it's going to just be t of n. And just remember the t of n is our kind of general function on this side. So t of n and f of n mean the same thing in this case. G of n is, on the other hand, is going to be the complexity category that we saw before. C is some constant that is going to make this g of n true. For example, if I had n squared on this side and I had n squared on that side, that would generally be true, but there may be a situation where you have 2n squared on this side and just n squared on this side because that's one of the g of n's. That wouldn't be true. So I would have to find a constant that causes this on the right side to actually grow faster than my 2n squared on this side. So you might say 2n squared or 3n squared or 15n squared, and then you would find a corresponding n, or rather n sub naught, that makes that true. So n's the size of the problem, and then n sub naught is the point at which the inequality becomes true. In other words, at some point that c times g of n will become and stay larger than f of n forever as n increases. So for proof problems on tests and homeworks that I give my students at least, you will be given the t of n, and you must prove what the Big O should be, what the Big O is. Okay, prove the Big O. The proofs are existential proofs, essentially. They're like a type of direct proof, and they just provide existence, essentially. They show that something exists. Meaning you just have to find a value for c and a corresponding value for n naught, for which that inequality right here is true. And you should also notice that the solution is not unique. For different values of c, you could have different values of n naught. And that's totally fine. You just have to find a pair, and as soon as you find a pair of n sub naughts and a c, you have provided enough proof. So, however, I have a pretty handy technique that is fast and works out for all the polynomial types, essentially would work for logarithms and other things too, although those might get a little bit trickier sometimes. But typically what I'm going to test my own students on are going to involve polynomials and subpolynomials. So when I say within polynomial, we're talking polynomials, and then also their linear and even constant could work, but constant's a little bit more trivial. So typically I'm going to use polynomials like these. So how do we solve these? So I use something called the promotion technique. This is a technique, I don't know that everyone calls it that, but this is a technique that is used by in many different books, and at least something similar to it would be used. So I like to do it this way. So here are the problems, the examples we're going to be working with. We have one example where we would say an algorithm has a running time, or a complexity, time complexity of 3n squared plus 4n plus 3. Another one has 2n to the fifth plus 3n to the second, 3n squared plus 5. And then 10n cubed, which is 10n to the third plus 2. So these are all possibilities. So my promotion technique that I like to promote, no pun intended, is copy the t of n on the left and the right side of an inequality, a less than or equal to inequality, because what I'm trying to do is I'm trying to get it in this form, so it looks like this part. I want my function it'll be whatever it is. Okay, the t of n is just going to be on this side. You don't change that. But I want to manipulate something on this side so that for some value, or for all values n greater than a certain point, this c times g of n is the format that I get on this side. So in other words, it's going to be some sort of constant times a function that is used with the big O. So for this example, you could intuitively just look at it and say, well, it's going to be some sort of constant times n squared because that's the largest term. That's what I want. My g of n is going to be n squared. So it's going to be some sort of c times g of n squared, and you have to kind of do it in a relatively rigorous way just so you don't mess up. But it's actually fairly simple. So copy the t of n on the left to the right of the less than or equal to symbol, promote each term on the right to the highest term, combine like terms, and now you have the format you need from the definition of big O, that is c times g of n. So our first question. So here's our first question. T of n equals 3n squared plus 4n plus 3. And I have my t of n, which is the f of n. That's my function I was dealing with, the runtime. Or not runtime rather, but the complexity function on this side, 3n squared plus 4n plus 3. I was given that. And I'm trying to prove it by putting it in the form c, some constant, times some sort of g of n. Now, you can, again, easily assume that the g of n is going to be n squared, so I'm going to try that. I'm promoting all of these terms. I basically copy-paste this onto the right side, but then promote each of the terms to the highest term. So the 4n becomes 4n squared, because the n squared is the highest term. 3n squared stays the same. And then this 3 just dangling on its own, that also becomes an n squared term, so it's 3n squared. So now, the cool thing is that since they're all like terms now, and we can agree that whatever's on this side is, in general, at some point going to grow faster than this side, we can just combine them by adding up their constant coefficients. So we end up with 10 n squared. And that's that c times g of n format that I needed. So the c is 10, and then we want to know where is it true. The n sub naught is pretty simple. So it would not be true for 0, because this side has a trailing constant, and even though these would get canceled out, you'd end up with 3 less than or equal to, and then all of this is 0, so we don't want that. But 1 is a value at which it would definitely be true past then, so this actually proves it. We would say we found a 10, which is c equals 10, or found a c rather, that c equals 10, and then we also have n naught equals 1. And just for a little bit of a visual, if I bring this over here, this is on desmos.com. It has our calculator here. I have my t of n, which is 3n squared plus 4n plus 3. You will notice that that is the red in here. And even though the red is actually, as far as the y is concerned, the red is actually bigger than the I'm calling it h of n here, but this is our c times g of n right here. So this is our 10 n squared. Even though this is larger than our 10 n squared at the point from 0, we usually don't care about the stuff below 0, but at 0, this is actually higher because ours is at 0. Our 10 times n squared is at 0, but our 3n squared plus 4n plus 3 is actually at 3. So that's actually bigger than ours. So that's why we need to make that statement that at a certain point it overtakes it. Now, where is that point? We said it was 1, and it does seem to make sense. It's kind of hard to see here, but if you zoom in pretty far, you'll notice that at some point, see that red goes under. That's the t of n that we were talking about, and then the blue surpasses it, and that happens at the point 110. Okay, so that's actually, the blue ends up being higher than that, and you can kind of look here. That blue is remaining larger than that, and will do so, it'll grow faster forever and ever. All right, so that should just give you a visual at least. So our question 2, for this example, we have 2n to the 5th plus 3n squared plus 5. Again, using my promotion technique, you can put that same t of n on this side, that's our f of n, and then we want to get it in the form c, some constant, times g of n. So if you just copy paste this to the other side, you're going to end up with 2 into the fifth, 3 into the fifth, 5 into the fifth, and then you can actually just add those together, get 10 into the fifth, and everyone's happy, right? So this again ends up being c equals 10 and n sub naught equals 1. Often, usually, the n sub naught for these polynomials, especially if they have a trailing constant, they're going to almost always have n sub 0 equals 1. But you can solve it. This is not the only technique you can use. If you have another one you prefer, or if you want to make a guess and just look at this and say, well, I think 3 into the fifth is going to be bigger than this, and then just find the point at which 3 into the fifth is bigger than that, and then you're good. Question 3, 10n cubed plus 2. This one again, 10n cubed plus 2 less than or equal to 10n cubed plus 2n cubed. That's 12n cubed. We end up with our c equaling 12, and the n sub naught equals 0. So if there's a trailing constant, your n sub naught is pretty much guaranteed to be 1. But remember, these are not unique solutions. The next thing that you should know is how would these functions, or how would functions like the above come to be in the first place? So I'm giving you functions and ask you what's the big O, but what does it look like when you compare it to code? So here's another technique, another skill you need as far as my tests and potential assignments are concerned. But it's good to know in any case, regardless of who your instructors are or what institution you're going to. This is determining the big O from code. So in this one, I'm not having you do proofs, but you may be asked on test or homework to look at code or pseudocode or a segment and then determine what's the big O. The great thing is that you may not fully use the exact techniques I do, but still arrive at the same conclusion. Now that might seem kind of crazy or a little bit flaky, but it's actually pretty cool. So when determining time, even though things like multiplication take longer at the hardware, or what we would consider the lowest level, they can be considered the same type of basic operation as addition or subtraction or greater than or equal to or not equal to or not or and or anything like that. So basic operations. So here's an example. The numbers for the following in the right column indicate the number of basic operations with respect to the size of the problem. For simplicity, we assume the problem size is passed in and is the variable n. So what I calculated, I would assume this function, okay, it's like kind of a pseudocode that looks a lot like Java or C++. But for this function, I take an input of n, and we assume this is our problem size, and the actual passing in of that input is just one operation, one basic operation. For this one, this line right here, now some of you might look at that and say, well, that's one operation, and that's fine. If you want to do that, that's fine, as long as it's as long as you can make a reasonable case when you get to the point where you decide what the big O is. But I say it's 2 because I go by the fact that this is a declaration, and then another basic operation maybe is an assignment. But you might decide that it's just 1, and that's fine too. It may even be better, who knows. So int y equals 10, that's another 2. So I'm doing the same as the above there. Now this is where it gets a little bit tricky, but pay very close attention to what's going on. And you have to think about the loop itself. Don't worry about what's in it. Think about the loop. So, and how many operations are being performed. We're not talking about how large x and y get. We're not worried about that. We're talking about how many times this occurs. And then that will affect what's inside, but let's worry about this right now. So how many times, or how many operations just independent of the loop would this be? Now I said it was 2, so I'm going to go with 2. And how many times is this executed in the loop? And the reality is that this part of the loop header is only done once. The one in the middle, we could say, is done n times, because it has to keep comparing it every time it goes back up to the top of the loop. And then the one over here, where it does the increment, that is also done n times. So in total, for the loop header, the loop itself, we have 2 plus n plus n, so that could be looked at as 2n plus 2. Now what's inside here, we have how many times this operation is done and what this operation is. I would look at this as an operation like this. So it's x an assignment is one operation, one basic operation, and the addition that has to be performed to get you the value for x to be reassigned is also another basic operation. And then this whole loop goes n times. So I would say it's that two basic operations each time, and you are doing it n times, so it's 2 times n. After the loop, we increment x one more time here. You might just say, oh, that's one basic operation. Now, I could say it's 2 because it's kind of doing x equals x plus 1. So you might decide it's 2, and that's fine too. Return x, there's another basic operation, I'm going to call it. Some people might even leave the return statement out. That's okay too. The key is that you got, especially the loop is very important, but that you're going to get something kind of similar to what I have. So the explanations here for the header, in case that wasn't clear, but in total, we add all of these all the way down. So these plus that, plus that, plus that, plus that. You get 1 plus 2 plus 2 plus 2 plus 2n plus 2n plus 1 plus 1. You end up with 4n plus 8. So that's our t event. And then you just basically, you could prove it if I asked you to, but I'm just asking you right now, what's the big O? Informally justify it. And you could say, well, the 4n is the largest term, so I know it's big O of n. And again, you don't say big O of 4n because we ignore the constant coefficients, and you don't say it's n plus 8 or 4n plus 8 because the any smaller terms, including trailing constants, are also disregarded. Okay, example 2. With this one, again, passing the value in, I'm calling 1, doing an initialization with the declaration is 2. In this case, there's 2 loops. We have to be a little bit cautious what's going on here. So this outer loop, this happens 2 times. And this is I less than n, and then this is I plus plus. Each of those is n times, so there's 2 of those. So that's 2n plus 2. Now the inner loop, independently, the inner loop is this happening twice, okay? So it is really what's going on in the outer loop, the 2n right here, this is happening the n outer loop, and then this thing happens n times. This right here happens n squared times, and then this happens n squared times as well, okay? So you end up with this 2n squared plus 2n. So this thing down here happens n squared times. And then at the bottom you have this return value of 1. So why is it the 2n plus 2 times n squared? Because the inner loop is 2n plus 2 on its own, just like the outer loop was. But then what you do is each iteration of the outer loop, it will affect what's going on in the inner loop. It's like the j keeps resetting. So this actually happens n times. This will happen n squared times. That will happen n squared times. So you end up with the 2n plus 2, the inner part, and it's done n times because that's how many times the outer loop iterates. So this is 2n plus 2 times n, so that ends up being the 2n squared plus 2n. Okay, so the full n iterations from the inner loop is what causes this to happen. Now, we would then add up all these terms here. You have 1 plus, or all these values rather, 1 plus 2 plus 2n plus 2 plus 2n squared, blah, 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 and then I put it in descending order of the power of the term, and I end up with 3n squared plus 4n plus 6. So we would say that this is a big O of n squared algorithm. So that is our big O. I don't think this sentence is written very well, but it's so our big O is n squared, and then the above is our t event. This is our t event right there. All right, so that's pretty much what I had for you. I just wanted to explain the document in case there was any lack of clarity, and I hope this was useful. Thanks.